Hi everyone, my name is Valerio Lorini and I'm going to present you the article Venice was flooding one tweet at a time that I wrote together with Paola Rufolo and Carlos Castillo. I'm a researcher at the Joint Research Center of the European Commission in Italy. Specifically, I work for the Copernicus Emergency Management Services that support local authorities and communities needing information to take critical decisions in the event of an emergency, such as natural disasters or humanitarian crisis. Our research can answer the following important topical questions. Is it possible to leverage real-time information from social media, fusing it with digital surface model derived from Earth observation data to provide a fast estimate of a flood extent? Satellite-derived products in urban environment are technically challenging for several factors, such as weather conditions, tall buildings, narrow roads, or reflective surface and pavements. LiDAR data can overcome such problems, but they are not highly available. Hazard maps generated by models are usually based on river flooding rather than extreme precipitations, as in the case of urban floods. A key advantage of our contribution lies in the real-time aspect of social media data, together with a physical model and Earth observation data, which are freely available. To demonstrate our starting methodology, we use the case of Venice flood in 2019. On the 13th November 2019, the mayor of the Italian city of Venice declared a state of emergency after an exceptionally high tides flooded the city. The maximum recorded water level was 189 centimeters on 12th November at 10:50 p.m. Hereafter, we refer to local time. The impact of the city was dramatic, with 2 fatalities, several damage to the crypt of the San Marco Basilica, 3 ferries sunk, and more than 2,000 claims for economic loss of totaling 9 million euros in damages by residents and businesses. The rapid mapping service of the Copernicus Emergency Management Services was activated by the Italian National Civil Protection Department on the 14th November at 1:15 p.m., as other exceptionally high tides were expected. The closest satellite image to the time and area of the event was acquired on 14th November at 11:13 a.m. Flooded areas were not visible completely visible due to the narrow streets of the city and the high off-nadir acquisition angle of the image, which was not vertical. The flood extent delineation that was delivered on 15th November at 9:18 p.m. shows the detected situation with an estimated flooded area below 30%. This significantly failed to capture the maximum extent flood later reported by the municipality, estimated at 82% of the pedestrian area. To test our workflow, we collected posts on Twitter using specific filters related to the Venice flood event between 12th and 14th November 2019 using available platform at the Joint Research Center. Our work aims to map the flood extent in a city, and therefore it is of the utmost importance that we geocode information as precisely as possible. We opted to use images filtered as relevant, identifying a recognizable point of interest like shops, monuments, street names, bridges, public transport stops, and their comparison with Google Street View. Once we collected 14,000 images, we used the convolutional neural network model for disaster image classification to classify the images of flooded locations. Finally, after the classification and the manual geocoding, we could identify 265 unique points. The focus of our research is to support the development of new products that could be made available within the first 24 hours after urban flood happened, when neither Earth observation-based nor authoritative maps are available due to technical challenges. The feasibility of such products is confirmed if we consider that the manual decoding process done by non-local personnel using Google Street View took 6 hours by one person. The social media flood points defined by latitude and longitude coordinates then were given a vertical attribute by sampling the available digital elevation models representing the 3D surface of the city. In order to study the quality and the scalability of the methodology proposed, we use 3 free of charge digital elevation models. The Shuttle Radar Topography mission, globally available from NASA with 30-meter resolutions, The Copernicus digital elevation model from the European Environmental Agency with a resolution of 10 meters, and then in Italy of the whole Italian territory with a 10-meter grid cell. Then as a second step, a default water depth of 80 centimeters was added to the ground vertical component based on visual inspection of the images, water above knees, passengers and doors. The third step of our methodology was to create a virtual water surface interpolating the social media flat points prepared in the previous step. We favored an inverse distance methodology, where the sample points are weighted during interpolation such that the influence of one point relative to another declines with distance. The fourth and last step of our methodology is the identification of the flooded area. This is obtained by comparing for each point of our map the digital elevation model and the virtual water surface generated at the previous step. When the water surface is higher, we assume the cell is flooded. The accuracy we obtain when determining whether a cell is flooded or not using maps that are freely available for the entire world is 61.3% at 10-meter resolution and 65.8% at 30-meter resolution. Using a more detailed country-specific map, we arrive at 87% resolution as shown in table. We can say that our experiment answered part of our research question in the affirmative, using both local digital elevation model data and the freely available Copernicus elevation model. The experiment demonstrates that it is possible to estimate quickly urban flooding extent using freely available resources at a fraction of the cost usually needed for satellite image processing. It must be noticed that the target accuracy for a mapping service like Copernicus rapid mapping is higher than 80%. And Earth observation accuracy in urban areas appears to be usually lower. Therefore, most of the times, urban floods are not even analyzed. It appears that while a high-resolution digital elevation model in our test show a high level of accuracy, even the worst case accuracy achieved during experiment could be valuable information for situational awareness. For instance, local emergency responders might use the flood extent map as a starting product and refine the map by gathering complementary in situ data based on their expertise and the knowledge of the distribution of the city's critical infrastructure. Our future work will aim at defining classes of cases and experimenting the timeliness and applicability of the methodology. An operational service could then estimate the applicability and the methodology within the first 24 hours and decide whether to add it or not to data available to crisis responders. If we consider the case of the Copernicus Emergency Management Services activation for urban floods in European cities, with the support of European-wide local experts, either volunteers such as VOST Europe or contractors that provide the service for a fee, where Google Street View is almost overall available, we suggest that systematic use of this methodology as a product to complement disaster risk management services. And at the same time, we hope to, and our intention is to continue to further analyze the scalability and future applicability to more cases. I thank you for your attention and I'm available for your questions. Thank you.